Hi, this is David Quatello with Siemens. In this Brain Shark, we'll be discussing the basics of switchboards. This course covers basic power distribution concepts and provides an overview of Siemens switchboards. You should have a basic understanding of electrical concepts to fully benefit from this course. And here are some of the legal trademarks we must mention. Upon completion of this quick step Basics of Switchboards course, you will be able to explain the role of switchboards in an electrical distribution system, define a switchboard according to the National Electric Code, the NEC, identify the main parts of a switchboard, identify various ways power can be brought into a switchboard service section, explain the difference between hot and cold sequence in relation to current transformers, identify the types of main and distribution devices available for Siemens switchboards, and identify the various models of Siemens switchboards. This course has 3 parts, plus a final exam. The first part is an introduction that covers basic switchboard concepts. The second part covers service entrance equipment concepts, and the third part covers Siemens switchboards. After each section, there will be a 5-question knowledge check. Power distribution systems are used in every residential, commercial, and industrial building to safely control the distribution of electrical power throughout the facility. Most of us are familiar with the power distribution system found in the average home. Power purchased from a utility company enters the house through a metering device. The power is then distributed from a load center to various branch circuits for lighting, appliances, and electrical outlets. Power distribution systems used in commercial and industrial facilities are more complex than those used in a single-family home and must be capable of handling high levels of current and voltage. Although some small facilities do not require switchboards, medium and large facilities commonly use switchboards to safely distribute power to transformers, panel boards, control equipment, and ultimately to system loads. Good power distribution systems don't just happen. Careful engineering is required to ensure that a power distribution system is capable of safely and efficiently supplying adequate electric service to existing loads and has the capacity required for future expansion. The role of a switchboard is to divide the incoming main current into smaller currents and safely distribute them as needed. The switchboard also provides switching, current protection, and metering for these currents. Although this general description applies to all switchboards, the voltages and currents involved vary with the size of the application. A small office building, for example, might require 120 volts for interior lighting and receptacles and 208 volts for heating, air conditioning, and exterior lighting. In this example, the utility company supplies 208 120 volt 3-phase 4-wire service. The main incoming line is divided into 4 feeders. The 2 outer feeders supply power directly to the 208 volt heating and air conditioning units. The 2 inner feeders are divided into a number of branch circuits. One set of branch circuits supplies 208 VAC power to exterior lighting. The second set of branch circuits supplies 120 VAC power to interior lighting and receptacles. The electric utility company uses a step-down transformer to supply power to a facility. There are a number of ways the secondary of the utility transformer may be configured. In this example, the utility supplies power from a transformer with a Y-connected secondary. The secondary winding of the transformer produces 208 120 VAC. Single-phase 120 is available between any phase wire and neutral. Single-phase 208 is available between any 2 phases. All 3 phases are connected to any equipment requiring 3-phase power. Incoming power is metered by the utility company. In this example, power is supplied to the building through a main service disconnect. A switchboard divides the power into 4 feeders for distribution throughout the building. This example shows an electrical distribution system for a medium-sized industrial plant. The incoming power is provided by a 480-277 volt 3-phase 4-wire system. There are 3 feeders. The first is used for various types of power equipment. The second feeder supplies a group of 480 volt motors. The third feeder provides power for 120 volt lighting and receptacles. In this application, the secondary winding of the utility transformer provides the 480-277 volts needed to power the system. The power from the utility company is metered and enters the plant through a distribution switchboard. The switchboard incorporates a main circuit breaker and circuit breakers for each of the 3 feeders. The feeder on the left powers a distribution switchboard, which, in turn, feeds a panel board and a 480 volt 3-phase motor. The middle feeder powers another switchboard, which divides the power into 3 3-phase 3-wire circuits. Each circuit feeds a busway run to 480 volt motors. The feeder on the right supplies 208 120 volt power to panel boards connected to lighting and receptacles. The National Electric Code, NEC, defines a switchboard as a large single panel, frame, or assembly of panels on which are mounted on the face, back, or both switches, overcurrent, and other protection devices, buses, and usually instruments. Switchboards may be accessible from the rear as well as from the front and are not intended to be installed in cabinets. As the definition indicates, switchboards enclose various devices. This illustration shows 2 switchboard sections, an incoming or service section and a distribution section that provides power to feeder and branch circuits. Circuit breakers mounted in these sections provide overcurrent protection. Some switchboards use fusible switches instead of circuit breakers. Switchboards include buses, which are metal bars mounted inside the switchboard to conduct power to various devices. A switchboard may include instrumentation. This instrumentation often consists of 1 or more meters designed to accept signals from sensors and other equipment, and then display values required for power monitoring and management. Another characteristic of a switchboard is that it may be installed away from a wall to provide access to the rear. Keep in mind, however, that this is not a requirement of all switchboards. Switchboards are built according to the standard set by Underwriters Laboratory, UL 891, and the National Electrical Manufacturers Association, NEMA, PB2. Basic requirements for switchboards are also covered in the National Electric Code. When selecting switchboards and overcurrent protection devices, it's important to know the supply voltage, maximum continuous current, and the available fault current. These factors are critical to the following switchboard ratings: voltage rating, ampere rating, and short circuit withstand rating. The voltage rating of a switchboard must be at least equal to the system voltage. The voltage rating can be higher than the system voltage, but never lower. The ampere rating refers to the current a switchboard or circuit protection device can carry continuously without deterioration and without exceeding temperature rise limits. The short circuit withstand rating refers to the level of fault current a switchboard can withstand for a specified time without sustaining damage. The standards for short circuit withstandability are set by Underwriters Laboratories, the UL Standard 891. Bus structures and bracing are designed to withstand a specified amount of current for a specified amount of time. The short circuit withstand rating of a switchboard is determined by the combined withstand, interrupting, and current limiting capabilities of the bus, overcurrent protection devices in the switchboard, and any overcurrent protection devices within or ahead of the switchboard that may supply and protect it. Interrupting rating is the maximum level of current that an overcurrent protection device, a fuse or a circuit breaker, can safely interrupt without damage under specified conditions. The interrupting rating of a switchboard, which incorporates a configuration of overcurrent protection devices, depends on the interrupting rating of the overcurrent protection devices and the rating method used. There are 2 methods used to determine the interrupting rating of a switchboard: the full rating method and the series rating method. The full rating method requires selecting circuit protection devices with individual ratings equal to or greater than the available fault current. For example, if 65,000 amperes of fault current are available at the service entrance, every circuit protection device must have a 65,000 amperes interrupting rating. Because the full rating method adds expense to a switchboard design, UL-listed series-rated switchboards are available for many applications at a lower cost. Like full rating, the series rating method also requires the interrupting rating of the main upstream circuit protection device to be equal to or greater than the available fault current of the system. But subsequent downstream circuit protection devices connected in series can be rated at lower values. For example, a building with 42,000 amperes of available fault current might use a breaker at the service entrance with an interrupting rating of 42,000 amperes and additional downstream breakers with a lower interrupting rating such as 18,000 amps. Series rated breaker combinations must be tested in series in order to be UL listed. Siemens series rated breakers are listed in the UL Recognized Components directory, those are the yellow books, in Volume 1. Selected series rated breakers are also listed in the Siemens SpeedFacts catalog. There are multiple elements that make up a switchboard. Included in the list of elements are a frame, buses, overcurrent protection devices, service metering, and outer covers. The frame houses and supports the other components. The standard Siemens switchboard frame is 90 inches high and 32 or 38 inches wide. An optional height of 70 inches with widths of 32, 38, or 46 inches is also available. Siemens switchboards have a depth measurement ranging from 20 to 58 inches. A bus is a conductor or a set of conductors that serves as a common connection for two or more circuits. The NEC requires bus bars to be located so that they are free from physical damage and held firmly in place. Bus bars are required to have phases in sequence, so an installer will find the same fixed phase arrangement in each termination point in any switchboard. This requirement is established by NEMA, the National Electrical Manufacturers Association. If a non-NEMA phase sequence is used, it must be marked on the switchboard. Unless otherwise marked, it's assumed that bus bars are arranged according to NEMA. The diagram illustrates accepted NEMA phase arrangements. Buses are mounted within the frame. Horizontal bus bars are used to distribute power to each switchboard section. Vertical bus bars are used to distribute power via overcurrent devices to the load devices. Bus bars are made of tin-finished aluminum or silver-finished copper. Bus bars may either be temperature rated or current density rated. The current density rating specifies the maximum current per square inch of a bus bar cross-section. This rear view drawing of a switchboard illustrates vertical and horizontal bus bar connections. The vertical phase bus bars appear to be reverse order because they are viewed from the rear, but are in the proper NEMA order as viewed from the front. A bus connector makes a mechanical and electrical connection between a vertical bus bar and its corresponding horizontal bus bar. In this drawing, the connector can be clearly seen on the neutral bus. Compression lugs provided on the switchboard accept properly sized incoming power cables. Splice plates are used to join the horizontal bus bars of adjoining switchboard sections, as illustrated in this rear view drawing. To make additional distribution sections easier to install when they are needed, the horizontal bus is extended and pre-drilled to accept splice plates. A new section is set flush against an existing section. The old and new sections are connected together with the splice plates. The extended horizontal bus is also referred to as through bus. Because the load requirements in downstream distribution sections are generally less than in upstream service sections, the capacity of the through bus is tapered or reduced downstream as the load falls off. The through bus is tapered to a minimum of 1/3 the ampacity of the incoming service mains. Full capacity or non-tapered through bus is available as an option. The ampacity of non-tapered through bus remains constant throughout the switchboard. Components that must be available to the operator are mounted on the front of the switchboard. This includes overload protection devices, such as circuit breakers and disconnect switches. These devices are mounted to the bus bars using straps connected to the line side of the devices. Cover panels are installed on the switchboard, so no live parts are exposed to the operator. The front cover is referred to as the dead front. The panels are also used as trim to provide a finished look to the switchboard. A product information label identifies the switchboard type, catalog number, and simplified drawings, such as one-line, block, or pictorial diagrams, are often used to show the circuits associated with a power distribution system. For example, this pictorial diagram shows a two-section switchboard. That concludes section 1. Now let's jump into a knowledge check. Question 1. The standard height of a Siemens switchboard frame is blank inches. Is it A, 68, B, 90, C, 110, or D, 120? Question 2. Switchboards can include which of these items? A, buses, B, overcurrent protection devices, C, power meters, or D, all of the above. Question 3. According to the NEC, switchboards blank. A, are accessible from the front only, B, are accessible from the rear only, C, are accessible from the front and or rear. Question 4. The blank rating refers to the current a switchboard or protection device can carry continuously without deterioration and without exceeding temperaturized limits. Is it A, ampere, B, interrupting, C, short circuit withstand, or D, voltage? Question 5. Siemens switchboard bus bars are made of tin finished blank or silver finished blank. Is it A, aluminum aluminum, B, aluminum copper, C, copper aluminum, or D, copper copper? Section 2 of the Basics of Switchboards covers service entrant equipment concepts. Switchboards are often used as service entrance equipment through which power enters the building. For example, this drawing shows a switchboard service section connected to a utility power source. This service section provides power to a switchboard distribution section and subsequently to downstream equipment. Switchboard used as service entrance equipment must be approved and labeled as such. Siemens switchboards are factory labeled as suitable for use as service entrance equipment when specified for service entrance application. Service entrance conductors must have a readily accessible means of being disconnected from the power supply. The NEC specifies that for each set of service entrance conductors, no more than 6 switches or circuit breakers can be used to disconnect and isolate the service from all other equipment. In this example, a single main circuit breaker can disconnect power from all equipment being supplied by the service. In this example, there can be as many feeder and branch disconnect devices as needed. In another example, a switchboard may be equipped with up to 6 circuit breakers to disconnect power from all equipment being supplied by the service. It is important to note that the 6 disconnect rule refers to the number of disconnects and not the number of poles. For example, in the following illustration, there are 18 poles but only 6 circuit breakers. 3 poles are mechanically linked together to form one disconnect device. This configuration allows the service to be disconnected with no more than 6 operations of the hand and complies with the 6 disconnect rule. Typical switchboards consist of a service section, also referred to as the main section, and 1 or more distribution sections. The service section can be fed directly from the utility transformer. In addition to the main disconnect, the service section usually contains utility or customer metering provisions. Several options are available to bring power into the switchboard service section. For example, cable can be brought into the switchboard from the top or the bottom. Cable can be brought into the top of the switchboard through conduit. If the cable has a large diameter and more room is needed, a pole box, available in 10-inch to 30-inch heights, can be added. In addition, a bus duct entrance can be provided when a busway connection is needed. Cable may enter through a conduit to a disconnect that is fed from the bottom. If the disconnect is top fed, a pull section can be added to the side of the service section to pass cable to the top of the switchboard. Depending on the cable bending space, cable can be connected directly to the lugs or to a cross bus. A cross bus brings the bus connections to the pull section eliminating the need to bend cables. Metering can either be hot sequence or cold sequence. This refers to whether or not power is still applied to the utility meter when the main disconnect is switched off. This drawing illustrates hot sequence metering. When the main disconnect is open, power is removed from the load, but power is still applied to the utility meter. This drawing illustrates cold sequence metering. When the main disconnect is open, power is removed from the utility meter and the load. Grounding is an important aspect of any electrical system and must be considered carefully. Any object that is electrically connected to the earth is grounded, but not all ground connections are intentional. A ground connection can occur accidentally as a result of faulty equipment or wiring. Proper intentional grounding, however, is essential to the safe operation of electrical equipment. There are two primary reasons for intentionally grounding electrical equipment. First, grounding reduces the shock hazard by minimizing the voltage differential between the parts of the system. And second, grounding provides a low impedance path to ground for fault current. The lower the impedance, the greater the current in the event of a fault. The greater the current, the faster the overcurrent device opens and removes power from the load. In this drawing, a switchboard is used as service entrance equipment and is connected to a 3-phase 4-wire service. Note that the neutral is grounded at the service entrance. This is accomplished by connecting the neutral to a ground bus bar. The ground bus bar is connected to the frame of the switchboard and the frame is connected to ground. The neutral disconnect link is left in place to supply a ground connection to downstream loads. This link is provided so downstream equipment can be disconnected from ground for testing and troubleshooting. The neutral is only connected to ground at the service entrance. When downstream equipment is used, the neutral is isolated in that equipment. The following illustration shows a service entrance switchboard connected to a downstream section. The neutral of the downstream section is connected to ground through the ground bus bar of the service entrance switchboard. The neutral is not connected to ground in the downstream switchboard. Notice also that the downstream switchboard does not have a neutral disconnect link. Neutral disconnect links are not required in switchboard used as non-service entrance equipment. Any downstream section fed from the second switchboard would also be connected to ground through the service entrance switchboard. A ground fault is a condition in which electrical current takes an undesirable path to ground. Typically, the current flows from a conductor to an adjacent grounded conductor or grounded surface. The most common type of ground fault is an arcing ground fault. In such cases, current often takes a high resistance path to ground and may flow intermittently or for a short duration. As a result, a ground fault often will not trip a circuit breaker unless it's been designed to sense ground faults. Nonetheless, ground faults can still be dangerous. In some applications, such as for selected locations in a residence, ground fault protection is required for life protection. In many commercial or industrial applications, ground fault protection is required to protect equipment. According to the NEC, ground fault protection of equipment must be provided for solidly grounded Y electrical services of more than 150 volts to ground, but not exceeding 600 volts phase to phase for each service disconnecting means rated 1000 amps or more. When ground fault protection is incorporated into a switchboard, it's often through use of circuit breakers with ground fault protection. One way a ground fault protector works is with a sensor around the ground conductor, normally the neutral to ground strap. This is referred to as the direct method. When a line to ground fault occurs, current flows through the sensor. When the fault current reaches the threshold setting of the ground fault protection equipment, a shunt trip opens the circuit breaker. Another way a ground fault protector works is with a sensor installed around all the circuit conductors, including the neutral on 4-wire systems. This is referred to as the zero sequencing method. When there is no ground fault, the sum of all the currents detected by the sensor is zero. When a ground fault occurs, it causes a current imbalance that is sensed by the protection equipment. When the fault current reaches the threshold setting of the ground fault protection equipment, a shunt trip opens the circuit breaker. Another approach is the residual method, which requires separate sensors to monitor current on all 3 phases, and the neutral on a 4-wire system. With this system, When there is no ground fault, the vector sum of the currents is 0. If a ground fault is sensed, however, a shunt trip opens the circuit breaker. Ground fault protection is often provided through an optional feature of a circuit breaker. In such cases, the circuit breaker is frequently equipped with fixed or variable settings for ground fault pickup, the level of ground fault current required to trip the breaker, and ground fault time delay, the interval of time the breaker will remain closed after a ground fault is sensed. These settings are useful for coordinating protection throughout a facility. Ground fault protection can also be supplied with some disconnect switches, such as the bolted pressure switch shown. Typical switchboards require one or more service main disconnect devices. A main disconnect device is mounted into a service section and feeds one or more distribution sections. In some applications, the main service disconnect is required to be located remote to the distribution portion of the equipment and is considered a remote main. The service section of Siemens switchboards can accommodate a variety of main protective devices. Depending on the switchboard model and customer requirements, the main protective device may be a vacuum brake fusible switch, a high contact pressure HCP fusible switch, fusible bolted pressure switch BPS, molded case circuit breaker MCCB, insulated case circuit breaker ICCB, or low voltage LV power circuit breaker. One type of protective device is a Siemens vacuum brake fusible switch. Vacuum brake fusible switches are available in ratings up to 1200 amps. Siemens high contact pressure HCP fusible switch is another device that can be used in the service section as a disconnect device. Visible contacts provide a visual indication concerning the state of the switch before servicing. HCP fusible switches are available with ampere ratings from 400 to 1200 amps. HCP fusible switches are suitable for use on systems with up to 200,000 amps of available fault current when used with Class J or Class L fuses. A fusible bolted pressure switch BPS can also be used as a main disconnect. Bolted pressure switches are available with ampere ratings from 800 to 6,000 amps. Siemens offers a wide variety of thermomagnetic and solid-state circuit breakers with continuous current ratings up to 2,000 amps. These circuit breakers are available with a wide range of features and accessories. Siemens WL family of circuit breakers has been designed to address the increasingly demanding requirements of today's power distribution system and incorporates the following characteristics: high reliability, compact size, ease of use, modularity of design, flexibility of system communications, safe-oriented features. The molded case circuit breakers discussed earlier conform to the UL 489 specifications. This specification also covers a category of molded case circuit breaker commonly referred to as an insulated case circuit breaker, the ICCB. ICCBs are generally used in switchboards and may be fixed mounted or drawer out mounted. Another category of large circuit breaker is the low voltage LV power circuit breaker. LV power circuit breakers are generally drawer out mounted and may be used in switchboards or switchgear. LV power circuit breakers intended for the U.S. market conform to American National Standards Institute, the ANSI, standards C37.13, C37.16, C37.17, and C37.50, and the National Electrical Manufacturers Association standard SG3. The corresponding UL specification for LV power circuit breakers is UL 1066. Siemens WL family of circuit breakers includes both ICCBs that conform to the UL 489 specifications and LV power circuit breakers that conform to UL 1066 and corresponding ANSI and NEMA specifications. WL UL 489 circuit breakers have a rated maximum operating voltage of 600 volts and are available in 3 frame sizes with frame ratings from 800 to 5,000 amps. All 3 frame sizes have fixed mounted and drawer out mounted versions. WL UL 1066 circuit breakers are generally used in switchgear as drawer out mounted breakers, but may also be used in switchboards. These breakers have a rated maximum operating voltage of 635 volts and are available in 2 frame sizes with frame ratings from 800 to 5,000 amps. The distribution section receives power from the service section and distributes it to various downstream loads. Depending on the design of a specific switchboard, the service section cabinet may be deeper than the distribution section. This is due to the size of the main disconnect device and associated bus requirements. The rear of all sections align, so the switchboard may be installed against the wall. This is referred to as a rear alignment. Switchboards can also be front and rear aligned if the depth of the service section and distribution section are the same. In some switchboards, the circuit protection devices and bus may require a deeper cabinet. In other switchboards, extra depth may be added on as an option. Like the service section, the distribution section accommodates a variety of fusible switches and circuit breakers. The specific devices and ratings available depend on the switchboard type and the requirements of the electrical system. In addition to these devices, motor starters are sometimes included. You've just completed section 2, so let's go ahead and do a knowledge check. Question 1. Which of these devices can be used as the main protective device in a Siemens switchboard? Is it A, HCP fusible switch, B, insulated case circuit breaker, C, LV power circuit breaker, D, molded case circuit breaker, E, vacuum brake fusible switch, or F, all of the above? Question 2. The blank section of a switchboard receives power from the service section and distributes it to various downstream loads. Is it A, distribution, B, main, C, service entrance, or D, utility? Question 3. The blank rating refers to the maximum current a protective device, such as a fuse or circuit breaker, can safely interrupt. Is it A, ampere, B, interrupting, or C, overcurrent? Question 4. The blank rating refers to the level of fault current a piece of equipment can withstand for a specified time without sustaining damage. Is it A, ampere, B, continuous current, C, interrupting, or D, withstand? Question 5. The blank rating method requires a main circuit protection device that is equal to or greater than the available fault current, but subsequent downstream circuit protection devices connected in series have a lower interrupting rating. Is it A, full, B, partial, C, series, or D, none of the above? We're now into the last section of the Siemens Quick Step Basics of Switchboards, and this part of the course covers Siemens switchboards. Siemens manufactures a wide variety of switchboards. The type of switchboard selected is determined by a variety of factors, such as space, load, and environment. In addition to meeting present loads, the switchboard should be sized to accommodate reasonable future load additions. The continuous rating and through bus can be sized on the basis of anticipated future load demand. Trip units or fuses of lower ratings can be installed to meet present load demands and change in the future as load increases. SB1, SB2, and SB3 switchboards are built to UL 891 and NEMA PB2 standards and provide the rugged construction and service flexibility necessary in systems for industrial plants, high-rise complexes, hospitals, and commercial buildings. SB1 switchboards are designed for the shortest lead times and for applications where floor space is at a premium. The rear of all sections align so the switchboard can be installed against the wall. An SB1 switchboard incorporates front connected main protective devices and through bus ratings up to 2000 amps and 600 volts. In comparison to SB1 switchboards, SB2 switchboards can incorporate additional features. SB2 switchboards can have extra depth behind the busing in each distribution section, can be front and rear aligned, and can handle up to 4000 amps and 600 volts. These switchboards may also include insulated case circuit breakers and density rated busing. SB3 switchboards are designed for custom options. For example, SB3 switchboards can incorporate busway and transformer connections, rear access, custom utility metering provisions, and many other options. Typical switchboards require one or more service main disconnects. These main disconnects are mounted in a service section that typically feeds one or more distribution sections. In some applications, the main service disconnect must be located remote from these distribution sections and is considered a remote main. The accompanying chart compares the main fusible switches or circuit breakers available for the SP1, 2, and 3 switchboards. In addition to the main disconnect, the service section usually contains utility metering provisions. Hot sequence metering, which is current transformers on the line side of the main disconnect, is normal. But cold sequence metering, current transformers on the load side of the main disconnect, can also be furnished. For either hot or cold sequence metering, the current transformers provided by the utility company are mounted in a separate compartment. The compartment is built to utility company standards with hinge doors and provisions for metering equipment provided by the utility. The service section can provide space for customer metering. Either analog or digital metering can be mounted in the service section along with the main disconnect. A separate section is only needed if a large or unusual number of instruments are required. SP1, SP2, and SP3 distribution sections are constructed with generous top and bottom gutters. In cable entrance sections, no obstruction is less than 8 inches above the floor, and no live bus bars are located less than 10 inches off the floor, so there's plenty of room to run cables into a distribution section. Standard bolted gutter covers give complete access to load conductors. Hinged gutter covers can be furnished where quick access to load conductors is desired. All distribution sections contain louvers at both the top and bottom to assure pool operation. Because all distribution sections can accommodate any combination of panel-mounted branch devices, future system modifications are easier to handle without adding switchboard sections. Installing additional distribution sections is simpler because the through bus in each distribution section is extended, and the end is pre-drilled to accept splice plate bolts. The accompanying chart outlines SP1, SP2, and SP3 branch devices. Siemens rear-connected RCS switchboards feature individually mounted branch and feeder devices. Because of this method of mounting, access to outgoing cable terminations must be from the rear of the switchboard. Bus bar extensions from the feeder devices are run back to the rear of the unit for easy access. The front and rear of all sections align. Both indoor NEMA 1 or outdoor NEMA 3R construction is available. RCS switchboards accommodate systems up to 6,000 amps, 600 volts maximum in any 3-phase, 3-wire, or 3-phase, 4-wire configuration. The main bus can be specified for 600 to 6,000 amp rating. RCS switchboards use WL insulated case UL489 or LV Power UL1066 circuit breakers with draw-out mountings and continuous current ratings from 400 to 5,000 amps for main and branch devices. The modular design of the Siemens Integrated Power System IPS switchboards allows the customer to integrate electrical distribution equipment, power monitoring, and environmental controls that typically mount in multiple enclosures into one switchboard lineup. Customers have the freedom to configure an arrangement that best fits their individual needs. Optional factory-installed interconnection wiring is available to further reduce installation time. IPS switchboards are built to UL 891 and NEMA PB2 standards. IPS sections have a standard height of 90 inches. Optional 70-inch high sections are available. The minimum depth of IPS sections is 13 3/4 inches. Optional depths of 20, 28, and 38 inches are available, and these optional depths may be required depending upon the components installed. IPS switchboards consist of one service section and one or more distribution sections that are cable connected. However, IPS switchboards are also available with through bus and pull sections. IPS switchboards accommodate systems up to 4,000 amps, 600 volt maximum in 1-phase 3-wire, 3-phase 3-wire, and 3-phase 4-wire configurations. Examples of IPS switchboard components that can be included to meet customer requirements include lighting panel boards, power monitoring devices, distribution transformers, access communication, lighting contactors, lighting controls, heating, ventilation, and air condition control, building management equipment, programmable logic controller, PLC, automatic transfer switch, motor starters, and backup generator. Siemens generator switchboards meet the market need for quick connection of a generator for temporary backup power. The most common applications of these switchboards are retail stores with perishable goods, nursing homes, and hospitals. However, these switchboards can also be applied to many other commercial applications where a power outage can result in increased cost or loss of revenue. Siemens generator switchboard features include all standard switchboard features, a Crouse-Hinds Quick Connect cam locks for quick primary connection method, standard mechanical lugs suitable for Type W welding cable for a secondary connection method, NEMA 1 and NEMA 3R enclosures, trapdoor on NEMA 3R enclosure to maintain rating with cables connected, labeled phases and ground connections, bus connection between generator breaker and plug-in quick connects, mechanical interlocking with normal breaker, removable screw cover for covering quick connects when not in use, and may be provided as a standalone unit or hard bus in traditional switchboard lineup. The generator breaker can be connected to the normal main switchboard by cable in retrofit applications or hard bus in new construction applications. The generator breaker is key interlocked with the main breaker in the normal switchboard lineup. The switchboard can be rated suitable for service entrance. Crouse-Hinds Quick Connect cam locks are provided in a compartment with a screw cover that can be easily removed to gain access to the quick connects. One end of each quick connect is attached to the switchboard and the other end attaches to the generator cable. In addition to the quick connects, standard mechanical lugs are provided as a secondary method of connection. The mechanical lugs are rated for Type W welding cable, which is common in generator applications. The switchboard generator breaker can be connected to a new or existing switchboard lineup either by cable or hard busing. Siemens Solar-Ready switchboards provide a solution for both AC and DC commercial solar applications. In addition to all standard switchboard features, optional viewing windows are also available for an additional level of safety when working with inverter inputs. Siemens switchboards meet all utility and code requirements. Siemens Super Blue Pendant switchboards are service entrance switchboards with the main service disconnect and distribution devices contained in a single unit. Super Blue Pendant switchboards meet Electric Utility Service Equipment Requirements Committee (USERC) specifications. The metering compartment has provisions for mounting a utility meter on the door. These switchboards also have test block provisions, use buried hot sequence utility metering, and have a fully bused power company current transformer compartment. The main service disconnect can be fusible 400 or 600 amp vacuum brake switch with a maximum interrupting rating of 200,000 amps, or a 400, 600, or 800 amp circuit breaker with a maximum interrupting rating of 65,000 amps at 240 volts and 50,000 amps at 480 volts. Distribution kits are optional and field adaptable with ratings of 400 to 800 amps. Up to 40 branch circuit provisions are available with an 18 branch circuit minimum. Siemens multi-metering switchboards are designed for applications where multiple utility meters are required. These applications include shopping centers, office buildings, and other buildings with multiple tenants. Siemens offers two types of multi-metering switchboards, SMM and MMS. Siemens SMM switchboards are designed to meet USERC specifications. The switchboard main service is rated up to 4,000 amps for the following services: 120 240 volt, single phase 3 wire, 240 120 volt 3 phase 4 wire, 208 120 3 phase 4 wire, and 480 277 3 phase 4 wire. SMM switchboards have the following additional characteristics: UL listed and labeled, hot sequence meeting standard, cold sequence optional, test blocks are standard, copper or aluminum bus available, 65,000 amp symmetrical bracing standard, higher bracing is available, type NEMA 1 or 3R enclosure, it meets UL 891 and NEMA PB2 standards, and ring type meter cover design. Siemens MMF switchboards provide a high quality multi-metering solution for areas where USERC compliance is not necessary. The switchboard main service is rated up to 4,000 amps for the following services: 208 120 3 phase 4 wire and 480 277 3 phase 4 wire. MMF switchboards have the following additional features: hot sequence meeting standard, cold sequence optional, 50,000 amp symmetrical bracing standard, higher bracing is available. All meter sockets are pre-wired, for 100, 200, or 320 amp sockets. Copper or aluminum buses available. Units are front accessible. Type NEMA 1 or NEMA 3R enclosure. Available with optional cable pull sections. Meter sockets include lever type manual bypass. Common depth for main and metering sections available upon request. Ringless type meter cover design. This slide lists specifications you need to know when planning a switchboard purchase. Other information may also be required. Keep in mind that the specifications developed for an application should take both present requirements and future needs into consideration. Things to consider include incoming voltage and configuration, incoming power protection requirements, available space and environmental considerations, system certification requirements, number and types of sections required, enclosure requirements, NEMA type, section alignment, accessibility and paint, shipping and lifting considerations, bus material, ratings and tapering, means of routing and connecting for the incoming service, utility and customer metering requirements, indicating light requirements, shunt trip requirements, key interlock requirements, types and ratings of the main and branch protective devices, fuse requirements, ground fault protection requirements, requirements for additional equipment to be mounted in the switchboard, and installation and service requirements. Let's get into our last knowledge check before the final exam. Question 1. SP1 switchboards are blank aligned. Is it A, front, or B, rear? Question 2. The modular design of Siemens blank switchboards allows the user to integrate electrical distribution equipment, power monitoring, and environmental controls that typically mount in multiple enclosures into one switchboard lineup. Is it A, IPS, B, SP1, C, SP2, or D, SP3? Question 3. SP1 switchboards have a maximum through bus rating of blank amps at 600 volts. Is it A, 1000, B, 2000, C, 4000, or D, 6000? Question 4. Siemens blank multimetering switchboard is designed to meet UCIRC applications. Is it A, MMS, or B, SMM? Question 5. The type of specialty service entrance switchboard that uses a quick make, quick break fusible switch as a main disconnect is A/AN blank service cubicle. Is it A, BCT, or B, SCT? Now it's time for our 20-question final exam. Question 1. Basic requirements for switchboards are covered in NEC article blank. Is it A, 210, B, 318, C, 408, or D, 770? Question 2. Which of the following statements is true according to the NEC definition of a switchboard? Is it A, switchboards are accessible only from the front? B, switchboards may be accessible from the front or from the rear? C, switchboards are intended to be installed in cabinets? Or D, switchboards usually do not contain instruments? Question 3. A blank is a conductor that serves as a common connection for two or more circuits. Is it A, conduit, B, frame, C, panel, or D, bus? Question 4. The standard height of a Siemens switchboard is blank inches. Is it A, 32, B, 38, C, 72, or D, 90? Question 5. The correct NEMA phase sequence for a vertical bus as viewed from the front left to right is blank. Is it A, ABC, B, ACB, C, CAB, or is it D, CBA? Question 6. Two adjoining switchboard sections are connected together with blank. Is it A, vertical bus bars, B, compression lugs, C, splice plates, or D, cable? Question 7. A blank is used when cables fed from the bottom of the switchboard need to be routed to the top of the switchboard. Is it A, service section, B, pull section, C, routing section, or D, distribution section? Question 8. When blank metering is used, power is still applied to the utility meter after the service main has been switched off. Is it A. Hot sequence, B. Cold sequence, C. Top feed, or D. Bottom feed? Question 9. The neutral conductor is blank grounded at the service entrance switchboard. Is it A. Never, B. Always, C. Rarely, or D. Often? Question 10. The maximum number of switches or circuit breakers on service entrance equipment used to disconnect and isolate the service from all other equipment is blank. Is it A1, B2, C6, or D8? Question 11. NEC Article 230.95 requires ground fault protection of equipment for solidly grounded Y electrical services of more than 150 volts to ground, but not greater than 600 volts phase to phase for each service disconnecting means rated blank amps or more. Is it A100, B1000, C10,000, or D100,000? Question 12. Which of the following devices can be used as a main protective device in a Siemens switchboard? Is it A. Multicase circuit breaker, B. Fusible switch, C. WL circuit breaker, or D. All of the above? Question 13. Siemens WL family of circuit breakers includes both ICCBs that conform to the blank specification and LV power circuit breakers that conform to the UL 1066 specification. Is it A. UL 489, B. UL 1066, C. NEMA KS1, or D. ANSI C12.7? Question 14. The blank rating method requires selecting circuit protection devices with individual interrupting ratings equal to or greater than the available fault current. Is it A. Series, B. Full, C. Interrupting, or D. Withstand? Question 16. Siemens SB2 switchboards have through-bus ratings up to blank amps at 600 volts. Is it A. 2000, B. 3000, C. 4000, or D. 8000? Question 17. Siemens SB3 switchboards with depths up to blank inches may be installed against the wall. Is it A. 68, B. 58, C. 48, or D. 38? Question 18. Siemens blank switchboards can integrate electrical distribution equipment, power monitoring, and environmental controls that typically mount in multiple enclosures. Is it A. SB1, B. SCT, C. IPS, or D. SBS? Question 19. Super blue pennant switchboards are rated up to blank amps with a circuit breaker main. Is it A. 500, B. 600, C. 700, or D. 800? Question 20. Siemens blank switchboards are designed for applications where multiple utility meters are required and USERC specifications must be met. Is it A. SMM, B. MMS, C. IPS, or D. BCT? Well, that concludes the Siemens Quick Step Basics of Switchboards. I thank you again for your time and attention to the course material. Take care.